Hey folks, in this video we're talking about electromagnetic radiation, which sounds intense and sometimes it is. So in this video, I would like you to, or after this video, I'd like you to be able to define electromagnetic radiation and give examples of what electromagnetic radiation is. I want you to be able to explain what a photon is, and I want you to know that there is a relationship and be able to explain that relationship between the speed of light, frequency, and wavelength, and also the relationship between frequency and energy. And this is for electromagnetic radiation. Holy cow, that's a lot of stuff. Let's get rolling. Here's some new vocab. All right, so electromagnetic radiation, or abbreviated EMR. What is it? Well, it includes stuff like visible light, the stuff that I see. Things like radio waves, things that carry radios through the air. You know, turn on a radio in a car, play stuff. That's because we sent information through radio waves. I got too excited. Also things like X-rays, which are kind of scary. Are included in electromagnetic radiation. There's other things in there too, which we'll talk about them all. This, though, it is radiation or emitted particles that responds to both electronic and magnetic fields. That is why it is electromagnetic. It responds to both electronic and magnetic fields. And so there are many different types, as I have said a few up here. And so with those different types come different properties. For instance, visible light is not so bad for us, while getting bombarded with X-rays is pretty no bueno. So very different properties there. Similarly, I cannot see radio waves or X-rays, but I can see visible light. Different properties. These properties of electromagnetic radiation, they are defined by wavelength, frequency, and energy. These are like the three things that we define electromagnetic radiation by. And really, you only need one of these to be able to determine the others. And so all of these different types of electromagnetic radiation, they make up this thing that we call the electromagnetic spectrum, which we'll look at later. But what's also very important to know is that all types of electromagnetic radiation travel at the speed of light. So if you've ever gotten an X-ray, those X-rays that were fired through your skin, but not through your bones, those traveled at the speed of light. Anything that you see, those lights, the things that you see are coming at you. Those light colors are coming at you at the speed of light. And when a radio wave leaves an antenna to go to a receiver, it is traveling at the speed of light. All electromagnetic radiation moves at the speed of light. And we have a symbol C for the speed of light. And we say that the speed of light is of roughly 3.0 times 10 to the 8th meters per second. That's how fast it travels. It's pretty forkin' fast. So here is that electromagnetic spectrum. And so we can see there are a number of different things in here. We've got radio waves, microwaves, infrared, our visible light spectrum, which is actually only this tiny sliver in here. We've got ultraviolet light, X-rays, and gamma rays, and yep, pretty neat stuff. And so you may notice this squiggle down here that gets smaller and smaller, kind of like a slinky shrinking. Well, let's talk about that in a moment. What is electromagnetic radiation made of? Is it made of matter? Like atoms? Matter is made of atoms. Is electromagnetic radiation? I don't know. Think about it. Well, you thought about it. Hopefully, the answer is no. Light is not made of atoms. Light falls under the electromagnetic spectrum. It's part of the whole EMR family, and I can definitely say that light is not made of atoms. It is, in fact, made of these different kinds of particles that we call photons. Photons are like a unit of light. So just like I am made up of many cells, which are made up of many atoms, the light that is coming from the sun, we can think of as being made up of many little bits, which we call photons. It's kind of a weird concept. I was first told to think of them as little packets of energy. I don't know if that helped me. Maybe it'll help you. But they're very weird because they do not have, or are not considered to have, a resting mass like matter. All matter has mass, but photons are not considered to have any mass or weight. And so they're really weird too because they behave like a particle, like an atom, but they also behave like a wave, which is pretty weird stuff. This is something that's called wave-particle duality, and we're not going to dwell on too much, but it's pretty wild. And so it's unlike matter, which behaves as particles. And so this gives electromagnetic radiation some very unique properties. So there's some very wild experiments devoted to this. But we've shown, the scientific community, not me personally, that light can bend actually around corners. So it will bend slightly around corners in a process called diffraction. And this is actually what causes rainbows. Light coming down from the sun bends around rain droplets, and it gets split up, making those pretty rainbows. Light waves can also cancel each other out, and there's a super wild experiment involving a laser beam that sort of like makes itself disappear in places. It's pretty neato stuff. Pretty neat. Not the scope of this video, though. But here's a little visualization about that light bending around a barrier in a process called diffraction. Nifty. So what makes these different types of electromagnetic radiation unique? Well, as I've said before, both X-rays and visible light are electromagnetic radiation, but they have very different wavelengths and frequencies. And so these two properties are connected. We're going to discuss these first. We'll talk about energy later. So when one of these increases, the other must decrease. And that's what we call an inverse proportional relationship. They are inverse in that when one goes up, the other goes down. Let's talk about wavelength first. So wavelength we represent with this cool symbol lambda. It sort of looks like an upside down Y. It is a Greek character. And lambda, or wavelength, measures the length between crests of waves. Now you might say, what the heck is that? Well, we'll look at it in a second. But I'll tell you that wavelengths can range from tiny sizes like nanometers to very long, like kilometers in size. There's a huge difference. The wavelengths of electromagnetic radiation that our eyes see are only in a narrow gap between 700 to 400 or 400 to 700 nanometers. So a tiny little section of the entire electromagnetic spectrum. And so if we wanted to talk about what is a crest or a wavelength, well, here I've got two crests labeled. They are the high points on a wave. So our wavelength here is going to be the distance between those dudes. And we can see this upper wave that's shown has a much longer wavelength than this lower wave down here. The distance between crests is much shorter. This has a smaller wavelength. And so we can also look at our electromagnetic spectrum, and we can see that's what this squiggly line corresponds to. Our radio waves, if that dude would go away, hey, come back slide, has very long wavelengths compared to ultraviolet light, or X-rays, or in particular gamma rays, which have very tiny wavelengths. Those crests are very close together there. Cool. So let's talk about frequency, the other part of that relationship. Frequency is how often a wave repeats in 1 second. And it's measured in units per second, or inverse seconds, which we also call hertz, Hz. Little bit weird, but if we imagine that this mark measures 1 second, this thing would repeat and have a frequency of 1 per second. There's 1 wave per second. This dude down here, by contrast, would have made at least a little bit over 2 waves per second. So it would have a little bit of over twice the frequency of this wave. 2 waves complete in 1 second as compared to 1 wave per second. So this would be low frequency, and this would be a higher frequency wave. So these two are tied together by our friend, the speed of light. As I've said, they're inversely proportional. So here's one way we can express this, that wavelength is proportional to the inverse of frequency. So as I said, if one increases, the other decreases. Now they're related by the speed of light, which is a constant and cannot change. And we have this cool equation that wavelength times frequency is always going to be equal to the speed of light. This is an important equation that we're going to deal with more in our next video. But that's pretty neat. So as we look at this, we can use this equation to relate together all this fun stuff. And we can also, it's nice to look at the units here, because if we have frequency, which is measured in meters, wavelength, which is measured in meters, and frequency, which we measure in 1 per second, or inverse seconds, if I do meters times 1 over seconds, I get meters over seconds, which is just like the units measured for, or used to measure speed of light. Neat. I just like to look at units. I find them helpful. And so, yeah, we can remember that wavelength is measured in meters, frequency in 1 over seconds, and speed of light is measured in meters per seconds. So here we have that spectrum, and we can look at this guy and think, we have our long wavelengths down here and our short wavelengths on this side here. We have our low frequencies over here with long wavelength. So a big wavelength means a little frequency. And on this side, we'll have big frequencies, because a big frequency means a very little wavelength. One way that I remember this is I think about and I use my arm to make waves. So if I'm making nice, long, slow, chill waves, the gap between them is pretty small. I can't make too many of these waves before I pass in front of my face. But if I have a tight wavelength, then I go up and down a whole bunch of times as I move across. It's very frequent that I go up and down when my wavelengths are short. And so it's important to remember that all these dudes are traveling at the speed of light. Holy cow, that's a lizard in a kilt. And that's a lizard in a luau dress. That's beautiful. Anyway, continuing, we're going to talk about energy now and hopefully start to wrap things up. So energy is important because different photons have different amounts of energy. This makes a X-ray very different from a radio wave. High energy photons, like the X-ray and gamma ray, can be very, very dangerous. They can zap your skin and change the way your cells are put together. And this includes ultraviolet light, as I said, X-rays, and also gamma rays, which I didn't mention here. So energy and frequency are directly proportionate. When you have a high frequency, you have a high energy. And so, as I just said, when you have a high frequency, you make a lot of repeats as you go along. It also takes a lot more energy for me to zigzag up and down like this than it does for me to make a nice low frequency, long wavelength. So my long wavelengths with low frequency are very chill and have low energy. This is, as I said, directly proportionate. High energy and high frequency go together. And so with that, when frequency increases, so does energy. They are related together by Planck's constant, which is a constant, and does not change. So they use this equation to relate them. Energy is equal to Planck's constant, H, times V, or frequency. And so, if we look at this little guy here, we can imagine, where are the high energy waves going to be? And where are the low energy waves going to be? Why don't you pause the video and think about that now? Sick! Well, we know that we have low frequency here with a long wavelength. We know we have and that means that we're going to have low energy, rather. And we know we have high frequency and high energy at the opposite side. Neato! So, I want you to think about where are we going to find the light or types of electromagnetic radiation, I should say, with low energy. Where are we going to find the ones with high energy? And convert on the same note, where do we find which of these types has the highest frequency? And which of these types of electromagnetic radiation has the lowest frequency? Pause the video, think about that now. Well, we have a handy guide for wavelength down here. And we know if our wavelength is small, our frequency is going to be high, and therefore our energy will be high. So we must have our high frequency, high energy dudes over here. And that means that our low frequency, low energy dudes are going to be over here. One thing I have noticed is that we have, as a species, put the word ray attached to our high energy things. So when you're pew-pew firing laser rays, they're going to have high energy. Well, anyway, that's the end of this video. I hope you understand kind of what light is now and how it's very different from like jars and other things made of matter. And I hope you have a greater appreciation for all the different types of electromagnetic radiation out there and how wacky and wild light really is. Ta-ta, and have a great rest of your life.